Assalamualaikum and greeting to all. My name is Hadzim Ashraff bin MAZLAN. My metric number is B019810248. So today I want to present about the Bachelor degree project BSM2. The topic is the study on heat transfer and pressure drop characteristic of nanofluid flowing in heat exchanger. So my supervisor is TS SITI BINTI MOKHTAR, and the faculty I am from is FTKMP. First thing first, we look at the table of the content. We have the introduction, problem statement, objective, scope, literature review, methodology, result, conclusion, Gantt chart, and lastly reference. So the introduction, why nanofluid? So electronic devices are getting miniature day by day, and it leads to development of integrated circuit of ultra large scale magnitude. The consequence of increased power density and extreme heat flux, long-term reliability and efficiency is hampered as conventional liquid fail to provide desired that removal from high heat flux generating electronic devices and heat exchanger. This research use nanofluid to combat this problem. So basically, nanofluid is a thermal engineered fluid capable of giving remarkable heat transfer improvements than the conventional fluid. So next, we go to the problem statement. In recent years, a surge in interest in heat transfer improvement, employing nanofluid in straight channel as existing technologies shrink in size and performance. As a result, several researchers have investigated the development of microchannel heatsink by using water as a working fluid, making it very low in thermal conductivity and having a minor effect on the pressure drop value in the channel. Consequently, it would be an excellent opportunity to examine the impact of using a different concentration of nanofluid, such as water CEO, in the microchannel heatsink, which may increase the rate of pressure drop outcome. So next, we go to the objective. Firstly, the objective is to study the pressure drops in microchannel heatsink using different concentration of water CO nanofluid. Second, to perform a CFD simulation related to pressure drop in unseized flow fluent using different concentration of water CO nanofluid. Lastly, the objective is to analyze the effect in pressure drop using different concentration of water CO nanofluid in CFD simulation. Next, we go to the scope of research. The type of nanofluid will be used water CO with a concentration of 1% until 5%. The channel which will be used in a straight channel, and the material of the channel is aluminium. The CFD simulation will be conducted in unseized flow fluent software. The heat flux will be at 1,000,000 watt per meter square at the heated source surface. The temperature of the fluid at inlet around 20 degrees Celsius. So the literature review behind the claim from Rimbaud and al. 2014. The topic of the research is experimental investigation of COO water nanofluid flow and heat transfer inside a microchannel heatsink. It states that an increase of the pressure drop and the friction factor with respect to water. This increase can be as high as 70%, 25%, and 30% respectively for the 4.5%, 1.03% and 0.2% particle volume fraction. From Ashraff and al. 2017, the experimental investigation of heat transfer and pressure drop in a straight mini channel heat sink using COO water nanofluid. So it states that the conjugate heat transfer and fluid flow characteristic in a rectangular microchannel heatsink using two types of nanofluid, COO water and COO EG. A new model has been used to calculate the dynamic viscosity and thermal conductivity of nanofluid. They discovered that the high aspect ratio is more desirable, and the employment of large value thermal conductivity nanoparticle result in improvement result. Next, from Hadzim and al. 2020, numerical investigation of nanofluid in a rectangular microchannel heatsink. The pressure drop and friction factor increase with rising nanoparticle concentration at n equal Reynolds number. However, if a trial made to increase Reynolds value, an increase occur in pressure drop, but friction factor decreases. And lastly, for Pegham-Bazadeh and al. 2014, performance of water-based CuO and Al2O3 nanofluid in a CuB alloy heatsink with rectangular microchannel. It states that CuO nanoparticles in water-based fluid were more prone to disposition than Al2O3 nanoparticle, although CuO was more efficient in terms of heat transfer rather than Al2O3. So next, we go to the methodology timeline. We have literature review, material selection, modeling, geometry, meshing, CFD simulation, comparison, and lastly documentation. First thing first, the material selection. The physical property. At the left side, we have the physical properties of water CuO nanofluid: 1%, 2%, 3%, 4%, and 5%. We have the density, viscosity, thermal conductivity, and specific heat. So the right side of the table, we have the physical property of the microchannel heatsink. The material used is aluminium. So next, we go to the modeling. So this is the modeling for the microchannel heatsink. The specification. So the length of the heatsink is 20 mm. Width of the heatsink is 20 mm too. The height of the heatsink is 2 mm. The channel height 0.2 mm. Channel width 0.1 mm. And total number of the channel is 11 channel. So the geometry, as you can see in the figure, the left side is the nanofluid and the right side is the microchannel. The nanofluid and the microchannel determined as solid, and the nanofluid determined as fluid. Next, we go to the meshing. We have the detail of patch conforming method, the scoping method, geometry selection. The geometry is used two bodies. The method is use tetrahedron algorithm, patch conforming, element mid side node, use global setting. So detail of the body sizing. The scoping method is geometry selection. The geometry, two bodies, suppress, no. Type, we use the element size. The element size I have used is 0.03 mm. So total of nodes is 166428. The elements produced 151487. So this is the surface boundary. We have I have stated 5 surface boundary on the single channel micro heatsink. So it's have inlet, outlet, symmetry, heated source, and internal wall. The CFD simulation, it have the reference value. So the reference value compute from inlet. area 1 meter square, density 1.225 kg per meter cube, enthalpy 0, the length is 4 mm, pressure 0, the temperature used 293 Kelvin, velocity 2 meter square, viscosity 1.7894, exponential 0.5 kilogram meter per second. The ratio is 1.4. So the boundary condition, we set the inlet velocity 2 meter per second, temperature 293 Kelvin. The boundary condition for heated source, the variable we set heat flux 160000 watt per meter square. So the number of the iteration for this study runs 1000 for the number of iteration. We go to the result and the discussion. Firstly, pressure drop versus distance. The pressure distribution inside the microchannel when various nanofluid are used, and the cross-sectional area of the microchannel heatsink remain constant. The pressure falls over the microchannel length of the heatsink for all concentration of nanofluid, as illustrated 1 concentration until 5% concentration. So the greatest pressure decreases occur at a concentration of water CO 5%. Naturally, this is owing to be increased density and dynamic viscosity of the water CO 5% physical properties. In the case concentration of water CO 1% nanofluid, the minimum pressure drop is obtained. This material has the lowest density and dynamic viscosity qualities due to the water CO 1% concentration physical properties. The graph stated that pressure drop related to distance. The graph show that the pressure drop along the microchannel heatsink. The figure show that the concentration of water CO 5% nanofluid have higher pressure drop than the others, and they decrease with the increase in the length of the microchannel heatsink. Also, pressure drop is clearly decreasing in an exponential trend for all nanofluid concentration. Next, the result for the temperature, contour, and the pressure related to temperature. First thing first, we talk about the contour. The distribution in the microchannel heatsink for several nanofluid with the same cross-sectional area are shown in the figure in the slide. 1% until 5% concentration. Additionally, for nanofluid flow, temperature value increases in the direction of the flow, reaching a maximum at the microchannel outlet. Water CO concentration of 1% and 2% exhibit nearly comparable temperature distribution. Since applying the water CO 3% concentration, the temperature transformed and nearly the whole length of the microchannel were chilled. However, the temperature distribution of the water CO 5% has entirely cooled across the cross-sectional area of the microchannel heatsink. The temperature distribution contour was affected by the differences in the physical parameter of each nanofluid. Next, we look at the graph pressure drop that's related to temperature. By referring to the graph, the trends are the same for all nanofluid studied, indicating that as pressure drop increase, the wall microchannel heatsink temperature decreases. In this situation, the water CO 5% concentration produces the greatest pressure drop and the lowest temperature result compared in the others. So next, the velocity contour for 5 concentration and the graph for pressure versus velocity. As you can see, the 5 contour of 1%, 2%, 3%, 4% and 5% for the velocity. While the length and size of the marginal heat sink are identical, the velocity distribution of the 5 nanofluid employ vary significantly. This is because the physical properties of each nanofluid vary. So in this case, the water CO of 1% and 2% concentration exhibit nearly equal velocity distribution and the lowest velocity compared to the others nanofluid. Water CO 3% concentration precipitated a significant shift in the velocity distribution contour. However, the water CO 4% concentration was the second highest, and the water CO 5% concentration velocity dispersion was the great. Next, we look at the pressure drop graph related to the velocity. So as you can see, as velocity increases, the pressure drop decreases. In a moving fluid, velocity and pressure are inversely related to each other. As the velocity of the fluid increases, the pressure falls, resulting in an overall reduction in pressure over the length of the microchannel. Next, we go to the surface Nusselt number contour result. As you can see, the 5 figure compares the surface Nusselt number distribution in the flow field of different concentration. The water CO concentration of 1% and 2% have almost comparable surface Nusselt number distribution and a smaller contact surface than the others nanofluid. Next, we go to the graph, the pressure drop related to the Nusselt number. So basically, the surface Nusselt number is the same in the water concentration of 1% and 2% and is less than of water CO concentration of 3%, 4% and 5%. However, varying the concentration of nanofluid result in various pressure drop with the same surface Nusselt number for all nanofluid. And lastly, the result is the surface heat transfer coefficient contour. For all 5 contour, the water CO concentration of 1% and 2% also have almost comparable surface heat transfer coefficient number distribution and a smaller contact surface than the other nanofluid. With the implementation of concentration of water CO 3%, 4% and 5%, the surface area of the heat transfer coefficient number began to get larger. So the graph between the pressure drop related to the heat transfer coefficient in comparison to other nanofluid, the microchannel heat sink operating with a concentration of water CO 5% has the highest heat transfer coefficient owing to its high thermal conductivity. However, when the heat transfer coefficient increases, the pressure reduces as well. So next, we go to the conclusion of this research. Firstly, through this study, the CFD data may be used to efficiently analyze the design without creating a large number of models. Hence, it's lowering the cost. However, as a prediction tool, the CFD is not wholly reliable and must be used with caution based on engineering understanding. Overall, the comparison of all concentration of water CO nanofluid demonstrates unequivocally that water CO 1% is the best for cooling because it exhibits the lowest pressure drop compared to the other nanofluid. This physical characteristic, concentration of water CO 1%, can fully exploit the advantage of increasing flow velocity, enhancing heat transfer, and lowering pressure drop. All simulations and analyses were conducted using ANSYS Flow Fluent software. And lastly, this project objective were achieved, and it can be used as a model for the future study paper. This is an example of Gantt chart that I have used for PSM1 and PSM2. And lastly, we go to the references. Firstly, from Rimbaud and al. 2014, experimental investigation of COO water nanofluid flow and heat transfer inside a microchannel heat sink, from International Journal of Thermal Science. Next, from Hassan and al. 2020, numerical investigation of nanofluid in a rectangular microchannel heat sink, from Journal of Mechanical Engineering Research and Development. Next, from Peghambazadeh and al. 2014, performance of water-based COO and Al2O3 nanofluid in a CUB alloy heatsink with rectangular microchannel, from Energy Conversion and Management. And lastly, from Ashraff and al. 2017, experimental investigation of heat transfer and pressure drop in a straight mini-channel heatsink using COO water nanofluid, from International Journal of Heat and Mass Transfer. I think that's all from me. Thank you for listening.